Welcome to day 43. Today, we're going to talk about a really simple but powerful idea in computer vision, the pooling layer. It's a key ingredient that helps neural networks generalize, letting them see the world a little bit more like you and I do.
So let me ask you this. Imagine you've built a fantastic cat detector, but then you show it a photo where the cat's ear is just one single pixel to the left of where it normally is, and poof, the model gets confused. It's no longer a cat. This is a real problem. Convolutional layers, for all their power, can be way too sensitive to the exact location of a feature. We need something to make them more robust. By the end of our time here, you'll get exactly how neural networks solve this sensitivity problem. You'll understand how they create smart, stable summaries of what they see.
So how do we fix this? Well, the core idea is surprisingly straightforward. We're not going to look for more features. Instead, we're just going to summarize the features we've already found. We're going to zoom out a little and focus on the bigger picture. Think about it this way. If you were summarizing a city map for a friend, you wouldn't list the exact GPS coordinates of every single car on every street, right? That's just noise. It's not helpful. No, you'd point out the important stuff, the big landmarks, the major districts. That's precisely what a pooling layer does for a feature map. And of course, there are different ways to summarize. The two most common are max pooling and average pooling. Max pooling is like pointing out the single most prominent landmark in each neighborhood, the tallest building, the brightest light. It hones in on the strongest signal in a small area. Average pooling, on the other hand, is more like describing the general character of that neighborhood. It takes an average of everything to get a sense of the overall presence of a feature. Okay, so that's the why. Let's dig into the how. The technical term for this whole summarization process is downsampling. Now, downsampling sounds technical, but really it just means making it smaller. We're taking a high-resolution feature map and creating a lower-resolution version, but, and this is the important part, we aren't just randomly throwing away pixels. We are very deliberately keeping the most important information. Here's how it works mechanically. We take a small filter, usually 2 by 2 pixels, and we slide it across our feature map. We typically use a stride of 2, so the windows don't overlap. For every 4 pixels the filter covers, it performs one simple calculation. It either finds the maximum value or the average. That one single number becomes a pixel in our new, smaller feature map. It's a systematic way of shrinking the map while keeping the essence. And the impact is huge. Look at this. A 6 by 6 feature map has 36 different values. After a standard pooling operation, it becomes a 3 by 3 map with only 9 values. The amount of data just dropped dramatically. And even more importantly, the model's focus shifts. It's no longer sensitive to a feature's precise location, but to its general presence in a region. So we've seen how it works, but why is this such a big deal in practice? What are the real-world benefits that make it a cornerstone of modern neural networks? Well, first off, it's incredibly efficient. In that little example we just saw, we cut the number of parameters by 75%. Now imagine that reduction in a network with millions of parameters. That's an absolute game changer for computation. It can be the difference between a model taking weeks to train versus just a few hours. But it's not just about speed. Pooling makes our models fundamentally more robust. It gives them what we call local translation invariance, which is just a fancy way of saying the model doesn't freak out if a feature moves a little bit. It also helps prevent overfitting, forcing the model to learn broader concepts instead of memorizing pixel patterns. And as a nice side effect, it suppresses noise by focusing only on the strongest signals. And you see this in action everywhere. Famous object detection models like YALO or SSD depend heavily on pooling. It's how they can take a huge image, shrink it down layer by layer, and build a more abstract understanding of what's inside. That's exactly what you need to do to draw a box around a car or a person, no matter where they are in the frame. All right, let's bring this all together with the one key takeaway. If you remember just one thing, make it this. Pooling layers down sample feature maps to create a more robust and efficient summary of an image's key features. Ultimately, the goal here is invariance. It's about making a model robust by teaching it to summarize what's important instead of having it memorize an exact location. That's how we get a model that sees a cat as a cat, no matter where it happens to be sitting.